This makes sense. Good? Still on break? A little bit. Now, I had a student in my other class ask me a really good question about, what about this rectangle right here? Is my formula going to fall apart? Because they were saying, wait a minute, this function g of y is on the other side of the y-axis. So is this formula actually going to work? Yes? Yes. Okay, so let's just talk about why it would work. The distance from here to here is what I'm interested in, right? So we know the distance from here to here is what? About 1. Yeah, don't worry about the numbers. Tell me in terms of functions. That's f of y, right? That's the red one. And the distance from here to here should be what? G of y, right? Now, if I subtract the two, you might be like, well, wait a minute, how's that going to give me the total distance? But look, if this is the y-axis, isn't g of y, isn't that negative? Right? That's going to be a negative number. But then you're subtracting it, which turns it back into positive. So it's actually going to measure this from here to here as a distance. You're going to take that distance and put it together with this distance, and it will still be the total length of the rectangle. So it still works. That's good news. That we don't have to worry about, oh, wait, if the rectangle drops into the other side of the axis, we have to change the formula or anything. Nope, it's always going to be good. The only thing you have to worry about is which one's on the right, which one's on the left. And in the other case where we have vertical rectangles, all you have to worry about is which one's on top, which one's on bottom. All right, I think it's time to see this in action, yeah? Now, you are not going to have the graphs given to you. All right, so I'm not going to provide you with the picture on the test or even in the homework. Well, the first couple of problems in the homework, they draw the picture for you. But after the first few problems, then you have to be able to graph them yourself. So we are going to have some basic knowledge of functions here in order to be successful. The standard stuff from college algebra, you know, power functions, like x to different powers, polynomial functions, quadratics, root functions, exponential, logarithmic functions. We need to know their basic shapes, trig functions. And we know their basic shapes, we'll be in business. So sketch the region bounded by these curves. There's two of them, right? Y equals 2 minus x squared, y equals negative x. So just by looking at this, are these functions of x or functions of y? Functions of x. The way you can tell is because it's solved for y, right? And that's what we've been doing our whole life. Solve it for y. That's your y is f of x, right? So it's just a matter of determining now which one is on top and which one is on bottom. So I'm already thinking right now I'm going to be using vertical rectangles because I have functions of x. So let's graph this first one. 2 minus x squared looks like, what is that? It's a parabola upside down, shifted up 2. All right, so we're going to go up 2. Boom, and we're going to go down. I don't know exactly where it hits. Well, I mean, we do, kind of. We set it equal to 0. We get positive and negative root 2 is where it would hit the x-axis, but that may not be even relevant to us right now. So there's one curve. And why don't I label this? This is y equals 2 minus x squared. And then we have another curve, y equals negative x, right? Which is basically, this is y equals x. Negative x is like 45 degrees the other direction, right? So it's going to look straight line, this. And maybe I should have extended that parabola down a little bit more. Like this. So do you see the region that's bounded by both? Yes? That's obvious to you. Here's our region. We want to know the area of that region. We know we're using vertical rectangles because they're both functions of x. So I'm going to draw at least one vertical rectangle in here. There's my little vertical rectangle. Okay? And just imagine this rectangle sliding through the area, right? The entire time it slides through, is the top function always the same? So as I move that through, is the parabola always going to be the one on top? Yes. Is the blue line going to be the one on the bottom? Yes. If you can do that, then you're pretty much in business. We'll see in another example that sometimes things get a little weird. We have to be careful. Over here, I'm going to take a little bit of time to kind of redraw that again. Here's my x-axis. This part's not super important right now, but later on, like on Thursday, this will actually help you if you can get used to drawing this to the side. Because we're going to, next class, we're going to take this and we're going to, just imagine taking this whole region and like, imagine this line right here. Just take that whole region and just start wrapping it around, three-dimensionally, wrap it around the x-axis. Can you see it coming out of the board and start going around this, not x-axis, around this line? And then back through the back side of the board and come back around. And that would create some solid, wouldn't it? So what's the volume of that solid? That's what we'll be doing next class. And to do that, to see it, it's better if you can draw it out here first. All right? So there we go. Now let me label some things. What is the function on top? 2 minus x squared. I'm going to call that my f function. So this is going to be my f of x is 2 minus x squared. And then my bottom function, which is this blue one, g of x, is negative x, right? And I'll take a little time to make some measurements here. The distance from the top of my rectangle down to the x-axis is f of x. And the distance from here, from the bottom to the x-axis is g of x. And if you want, you can actually put what they are. I just kind of didn't have enough room. Maybe I'll squeeze it in here. 2 minus x squared. And what we're interested in is this distance right here. And that distance should be the difference between them. So that's going to be the 2 minus x squared, take away the negative x. Do y'all agree? That's f minus g. At this point, you're pretty much ready to start setting up the integral. Because we know this is the formula, right? This is the integram. That's the thing we're going to have to integrate. But what's missing? What do we still not know? Well, dx, yeah, it's here though, right? This is always going to be dx. We don't know our limits of integration. We don't know a and b yet. So let's go try and find where these two guys intersect. Right? So we're going to find those two intersection points. We're interested in the x-coordinates of those intersection points. I'm stopping myself up here from being very inappropriate. That's why I'm giggling. All right. Intersection points. You said I do what to do this? Set the two functions equal to each other. So I'm going to be setting f of x equal to g of x, which means I'm setting 2 minus x squared equal to negative x. And what type of equation is that? Quadratic. How do we solve quadratic equations? Always get them equal to 0 first. Okay, so get everything to one side. So I'm going to move everything off the left side and move everything to the right, so it'll look like x squared minus x minus 2. I could have done everything on the left side, right? But I moved it to the right so that I could get a positive coefficient on x squared. That's why I chose it that way. And now, if need be, quadratic formula, but this factors. So I'm going to factor it. Minus 2 and plus 1. And that gives you your two solutions of 2 and -1, right? So I should intersect this point right here. This should be 2, and this should be -1. And that seems reasonable for my picture, doesn't it? Questions? All right, let's set it up. Ready for the integral. My integral should be so this green area right here is equal to the integral from -1 to 2, right? -1 to 2 of f minus g. So watch how I write this. Here's f minus g dx. I could use parentheses instead of brackets, but I just chose to use brackets. Let's take care of the inside there. What is that inside simplified to be? Minus x squared plus x plus 2. Can drop all the brackets and everything there. And that's an integral that you wish you would have had on your test, right? That's a very clean, easy, definite integral. Antiderivative of those things are pretty nice. But let's take it all the way. We may as well, right? So I'm going to continue that work right in here. So I take the antiderivative. I get -1/3 x cubed plus 1/2 x squared plus 2x. And then I bring in that little evaluation bar, -1 to 2. You agree with the antiderivative? And now plug and chug. So I'm going to plug in 2, plug in -1, subtract. So let's go with the 2. 2 goes in, 2 cubed is 8, right, times -1/3, so -8/3. Then I plug 2 in here. 2 squared is 4, half of 4 is 2, so plus 2. And then 2 here, we get 4. -1 goes in next. So -1 cubed is still -1, but then times -1/3, so negative and negative is positive, so 1/3. -1 squared is 1, half of that, it's just 1/2. And finally, -2. Okay. Let me try and drop all my parentheses here. -8/3 plus 6, I went ahead and put those together. -1/3 plus, no, not plus, I almost messed up. -1/2 plus 2. So distribute your negative through. And do y'all see these two go together? What's -8/3 minus 1/3? -9/3, but -9/3 is -3. So that's -3. So -3, let's add 6, so we would get 3, right? So we have 3, still have -1/2 plus 2, which is 5, take away 1/2, which is 9/2. Common denominator, done. So the area between those curves is 9/2. What do y'all think? Pretty straightforward? So far? Yeah. So really the only thing that's going to get more complicated are, the functions themselves and making sure you can graph them. And so let's move on to the next one. So example 2, sketch the region bounded by y equals root x, y equals x minus 2, and y equals 0. What are you thinking, vertical rectangles or horizontal? Vertical or horizontal? Are these functions of x or functions of y? These are functions of x because they're solved for y. I know it's backwards. Functions of x are always solved for y. Since these are solved for y, it appears that these are going to be functions of x. So it appears that we're going to use vertical rectangles. Let's start with the drawing the region. Square root of x. We're all very comfortable with root x. Kind of looks like a parabola that got cut in half and laid on its side, right? That's what square root of x is. I'll go ahead and put that here. Y equals root x. And then we have x minus 2. Diagonal, right? This is y equals x. Take away 2 moves it down 2 units. So we have something like this. We go down 1, 2, and draw a diagonal to the best of our ability. It's y equals x minus 2. So far, do we have a region? Not yet. Okay. Once I include this, yes, but at this point I don't. Have y'all ever used, like, I don't know, Photoshop or any of these photo editing softwares? They've got this little tool on it. It's a paint bucket. Y'all ever used that paint bucket on a computer? No? It's like if you go to a region, you click the paint bucket in here, it'll fill this region with that color. Right now, if I try and fill this region, it's going to overfill and go outside and go everywhere, right? It's not totally enclosed yet. So what we need is something else to enclose it, but we have one more piece of information here. Y equals 0. What is y equals 0? Flat line. Which way? It's the x-axis. Y equals 0. Right? That means your y coordinate is always 0. If your y coordinate is always 0, that means you're not up or down ever. Right? This is x equals 0. X is 0, y is 0. X is 0, y is 0. So we actually have the x-axis right here going this way. This is y equals 0. Now do we have a region that's enclosed? Yes, we do. Our region that's enclosed by all of them is this right here. Okay. Now everything so far has been setting up to be vertical rectangles. But do you see an issue? Mm-hmm. What issue do you see? Yeah, so if we start drawing rectangles in here, so here's my first rectangle. Let's just put it right here. So it's cut off right there at my hand, right? So we got that. Right here, blue one's on top, green one's on bottom, right? And that's good for any rectangle I draw all the way from here. But once I get to that corner point, right? Once I hit that corner and I'm over here, now the top one is the blue, but the bottom one is the red. So it's switched. How can we address that? We can do two integrals. We can imagine cutting this region into two pieces. We do this integral first, that'll give us that area. Then we do this integral from here to here, that'll give us that area. Do you understand the difference between the two? Okay, let's go ahead and do it. So I'm going to have this first integral over here. Imagine this little rectangle right here. Let's see if we can't figure out what that's going to be without going through like drawing it out over here. What do I still need in order for me to get the actual integral? The limits, right? So where does this start? I think it's obvious that it starts at 0, but it's going to end right here, isn't it? And you need to know that point.